By the term frequency response, we mean the steady state response of a system to a sinusoidal input, or we can also say the magnitude and phase relationship between the sinusoidal input and the steady state output of a system is referred as frequency response. For an LTI system, the frequency response is independent of the amplitude and phase of the input signal. Before starting this unit, you have to keep in mind that there are two assumptions which we assume to be true while dealing with frequency domain analysis of control systems. The first is the time constants are very small or almost negligible. And the other assumption we have already discussed is multiple times, which is for a sinusoidal input, we put the value of Laplace variable s equal to j omega. We simply ignore the damping factor sigma. There are a lot of control systems where frequency response is given priority over time domain analysis. For example, communication systems. The ATC in the watchtower communicates with the pilot with equipments which specifically works on VHF frequency band, and as such, the equipments which are utilized for doing so are specifically designed for this frequency band. There are other examples also, like audio amplifiers and speaker systems and filter design. There are other examples also where time domain analysis is more relevant compared to frequency response analysis, like nuclear power plants, medical support systems, and power converter control systems. Before moving forward, let us see some basic properties which will be utilized for frequency response analysis. I have taken a random transfer function s plus 1 divided by s square plus 3s plus 4. For frequency response, this transfer function will get converted into j omega plus 1 divided by 3j omega plus 4 minus omega square. The magnitude of this transfer function will be equal to under root of omega square plus 1 divided by under root of square of 3 omega plus within bracket 4 minus omega square bracket closed raised to the power 2. Phase of the transfer function is equal to tan inverse omega minus tan inverse 3 omega divided by 4 minus omega square. If you see carefully, the magnitude is actually equal to magnitude of numerator divided by magnitude of denominator, whereas phase is equal to phase of numerator minus phase of denominator. Now suppose if there are two signals which are multiplied, then their resultant magnitude will be equal to the product of magnitude of individual signals, and the resultant phase will be equal to the sum of two individual signals. Similarly, if the signal xj omega is divided by yj omega, then the resultant magnitude will be equal to the magnitude of xj omega divided by the magnitude of yj omega, and the resultant phase will be equal to the phase of x signal minus the phase of y signal. These are the basic properties which you might already know and will be used further quite frequently. Now let us analyze the frequency response of second order control system. We are quite aware about the standard form of second order control system. For frequency response analysis, we can simplify the expression of closed loop transfer function, which will eventually come out to be equal to 1 divided by 1 minus omega divided by omega n square plus j into 2 zeta omega divided by omega n. The magnitude of this transfer function can easily be found, which will come out to be equal to 1 divided by under root of 1 minus omega divided by omega n square, the whole being raised to the power 2 plus square of 2 zeta omega divided by omega n. The magnitude can also be represented in dB scale. Similarly, we can find the phase of the transfer function, which will come out to be equal to minus tan inverse of 2 zeta omega divided by omega n, the whole being divided by 1 minus omega divided by omega n raised to the power 2. Now, we will try to plot an approximate graph by using only these two equations. At low frequency, when the operating frequency is significantly smaller than the natural frequency, the magnitude is approximately equal to 1, and in dB scale it will be 0 dB. The phase in this case will come out to be equal to 0. The second case is when we take a random case, like suppose the operating frequency is exactly equal to the natural frequency. In this case, the magnitude will come out to be equal to 1 divided by 2 zeta, and in dB scale it will come out to be equal to minus 20 into log of 2 zeta, and the phase shift in this case will come out to be equal to minus pi by 2. And the third case is when we are having a very high frequency such that the operating frequency is significantly greater than the natural frequency. In this case, the magnitude will come out to be approximately equal to 1 divided by square of omega divided by omega n. Interestingly, when you convert this magnitude in dB scale, you will get the expression minus 40 into log of operating frequency plus 40 into log of natural frequency. This is actually a equation of line with slope minus 40 dB per decade. And the phase shift you will get in this case will be equal to minus pi. Now, after considering these three cases, we should be able to plot a rough graph of magnitude and phase of the transfer function at different frequencies. The graph will look like this. These graphs are also referred as frequency response magnitude characteristic graph and frequency response phase characteristic graph. Observing carefully the magnitude characteristic graph, you will realize that the amplitude provided by the transfer function decreases significantly after a certain value. In other words, we can also say that the system allows only certain frequency, and after a certain point, the transfer function begins to attenuate the incoming signal significantly. And that's why the shown characteristic graph is actually a graph of low pass filter. There are few parameters which every student should know. Students should know the proper definition of these parameters, the formulas to calculate different parameters, as well as their derivations. One such parameter is resonance peak, which is the highest value of the magnitude attained by the transfer function, and the frequency at which it happens is referred as resonant frequency. Another important parameter is cutoff frequency, and the last parameter is bandwidth, which is very closely related to the cutoff frequency. But let me make it very clear to you now. The definition which you are going to see for the cutoff frequency and bandwidth here are slightly specific, meaning that since we have considered low pass filter, the definition for cutoff frequency and bandwidth will be specifically meant for low pass filter. However, we can also say that these definitions will be valid for the standard second order control system, as by mere coincidence, a standard second order control system acts like a low pass filter. Let's see these parameters in detail. Resonant frequency is the value of frequency at which the magnitude characteristic of frequency response has peak value. We are aware of the formula of the magnitude of the transfer function. We have to simply differentiate the expression with respect to the omega, and then equating the expression to 0, we will get the expression of resonant frequency. If you are watching these lectures as if a movie is going on, then these lectures will not help you. You should take out a pen and paper and try to differentiate the expression with respect to omega yourself and see whether you are getting the same answer or not. For your help, I have already attached the short notes in the video's description where you can see all the steps of the derivation. The bottommost link is of the current unit. You will finally get the formula for resonant frequency to be equal to natural frequency multiplied by under root of 1 minus 2 multiplied by zeta square. Now you have to use a little bit common sense also, as frequency is a real quantity which cannot be negative, so the formula for resonant frequency is applicable only when the value of zeta is smaller than 1 divided by root 2. The second parameter is resonance peak. It is the maximum value of frequency response magnitude characteristic graph. The maximum amplitude can easily be found by putting the value of resonant frequency in the expression of transfer function magnitude, and by doing that you will get the resonance peak value to be equal to 1 divided by 2 zeta into under root of 1 minus zeta square. For all values of zeta which is greater than 1 by root 2, the resonant frequency will be assumed to be equal to 0 and the resonance peak to be equal to 1. And when the zeta is smaller than 1 by root 2, the resonant frequency will come out to be smaller than natural frequency and the resonance peak will be greater than 1. The cutoff frequency is the frequency at which the magnitude of the transfer function drops to 1 by root 2 times of its zero frequency amplitude. The last three words, which is zero frequency amplitude, is specific to this case only, as I have told you already that we are focused on second order control systems, which by mere coincidence comes out to be a low pass filter. We already know the formula for the magnitude of the transfer function. For finding the value of cutoff frequency, first we will put the magnitude to be equal to 1 by root 2. After that we will get an expression in terms of operating frequency omega and natural frequency omega n. Try to solve that equation yourself. You can take help from the short notes which I have attached in the video description. After solving, you will get the formula for cutoff frequency to be equal to natural frequency under root of 1 minus 2 zeta square plus under root of 4 zeta raised to the power 4 minus 4 zeta square plus 2. There is one more formula which is its linear approximation, which is equal to natural frequency omega n multiplied by minus 1.2 zeta plus 1.85. The fourth parameter or the last parameter is the bandwidth, which is the range of frequency from 0 to cutoff frequency. And again, this definition is meant for low pass filters only. Before you get confused, let us clear this confusion zone. Suppose we are having a computer system, then you will have input and output. Now suppose if you are applying an input with a magnitude of 1 and the amplitude of the output comes out to be greater than 1, for example 2, 4 or 7, then the control system will be acting as an amplifier. And if the amplitude comes out lesser than the amplitude of the input, then the control system will be referred as attenuator. The reference case is when the amplitude of the output is exactly equal to the amplitude of the input. For the reference case, the magnitude provided by the transfer function is equal to 1, which is actually equal to the amplitude of the output divided by the amplitude of the input, and in dB scale it is equal to 0 dB. Now if we try to put all these data in the graph, then we can see that 0 is the difference line and above it is the amplification zone of the transfer function and below that is the attenuation zone. In reality, bandwidth is the region of frequencies where the input signal power does not get reduced to more than half of its original power. This is the exact definition of bandwidth which you should keep in mind. However, interestingly, the definition of bandwidth changes in different subjects. If you try to Google the definition of bandwidth with respect to networking, you will get a completely different definition. Anyways, it will be better if we stick to our subject, control systems. The definition of bandwidth is actually related to the power of the signal. Power is directly proportional to the square of the amplitude of the input signal, and that's why for half power, we should have the amplitude equal to peak amplitude divided by under root 2. For better clarity, it will be better if we take another example rather than low pass filter. In this case, you can see we are having 2 minus 3 dB points in the characteristic graph. Here, you cannot say bandwidth is equal to the range of frequencies from 0 to the cutoff frequency. Such type of systems where the system allows certain frequencies, rejects low frequencies as well as high frequencies are referred as band pass filter. So, I genuinely hope at least now you are very clear why this definition of bandwidth is very specific in nature. If you are making short notes and if you try to correlate the time domain analysis parameters with the parameters which you study in frequency domain analysis, you will find that few parameters are quite similar. Like we are having damped frequency in time domain analysis. Interestingly, we are having resonance frequency in frequency domain analysis. Their formulas are also very similar. Similarly, we are having peak overshoot in time domain analysis, which is quite similar to the parameter resonance peak while we deal with frequency domain characteristics graph. There are few more points which are very helpful for you written in short notes that are self-explanatory. I hope you have enjoyed this lecture.